What the most dangerous thing in science is not ignorance, but certainty. You have lived inside a framework built over centuries. Physics, chemistry, biology, disciplines constructed with extraordinary care. And within that framework, you develop something more powerful than knowledge. You develop confidence. The kind of confidence that says, we know how the universe works. We understand the fundamental rules. Some things are simply impossible. From where I am transmitting, that confidence looks different. Not wrong, not foolish. Early, let me explain. In the early 21st century, humanity stood at the edge of a remarkable frontier. Quantum mechanics had been formalized for over 100 years. Its predictions were staggeringly accurate. Particle accelerators confirmed theoretical models with precision down to decimal places that would have seemed absurd to scientists of the previous century. You had mapped the genome. You had probed the structure of matter to scales previously unimaginable. You had sent machines beyond the solar system. You had every reason to feel confident. And yet, there was a pattern in your history that you recognized but rarely applied to your own moment. A recurring pattern. Every generation that believed it stood near the completion of scientific understanding was wrong. Not slightly wrong. Structurally wrong. In the late 1800s, prominent physicists believed physics was nearly complete. A few small problems remained. Small problems. Those small problems became quantum mechanics and relativity. Two revolutions that redrew the entire map. You knew this history. You taught it. And then, in the early 21st century, you did the same thing again. Not from arrogance, from success. Success is the most seductive reason to stop questioning. Here is where things begin to get interesting. Quantum mechanics is one of the most tested theories in the history of science. Its predictions are correct. That is not under dispute. But there is a difference between a theory producing correct predictions and a theory being a complete description of reality. This distinction was debated in your time. It was not resolved. Consider the measurement problem. When a quantum system is observed, its probabilistic wave function collapses into a single definite outcome. Physicists of your era agreed on the mathematics. They did not agree on what that mathematics meant. The Copenhagen interpretation said, do not ask what happens before measurement. The many worlds interpretation said, everything happens simultaneously across branching realities. Pilot wave theory said, there's a deeper layer beneath the probabilities, a hidden structure guiding events. 3 interpretations, 1 set of experimental results, all mathematically equivalent. You could not distinguish between them with any experiment available to you, which means your instruments were not yet capable of accessing the level of reality where the answer lived. Think carefully about what that means. If the answer existed at a scale or dimension beyond your measurement capability, then your certainty was not based on complete knowledge. It was based on successful approximation. Approximation at an extraordinary level of precision. But approximation. There's a concept that should have been more troubling to early 21st century science than it was. The concept of the observer effect, not the popular misunderstanding that human consciousness collapses wave functions. The actual phenomenon, that measurement itself, the act of interacting with a quantum system to extract information, changes that system. This was not a philosophical curiosity. It was a physical fact, and it raised a question your era approached carefully but never fully answered. What is the relationship between information and physical reality? This question sits at the intersection of quantum mechanics, thermodynamics, and information theory. By the time of your era, it had produced extraordinary results. Quantum entanglement. 2 particles maintaining instantaneous correlations regardless of distance have been confirmed experimentally, not theoretically predicted, confirmed, measured, repeatable, and yet your era was deeply cautious about what entanglement meant. Rightly so, in many ways, the speed of light limitation on information transfer remained intact. Entanglement could not be used for faster-than-light communication in any classical sense. That boundary held. But the boundary on what entanglement implied about the structure of reality, that boundary was far less clear. Some physicists in your era proposed that space itself might be emergent, not fundamental, that what you experience as 3-dimensional space could be a kind of projection, a macroscopic pattern arising from a more fundamental informational substrate. This was not mainstream, but it was not dismissed. Papers were published. Conferences were held. The idea had serious defenders with serious mathematical frameworks. If space is emergent, what does that mean for limits defined in space? This is the question that should make you pause. The speed of light is a limit defined within space-time. It is extraordinarily well confirmed within space-time. But if space-time itself is not the deepest level of physical description, if there is a more fundamental layer beneath it, then asking whether there are limits in that deeper layer is not a violation of physics. It is an extension of the inquiry. Your era had a habit of treating the current best theory as the final framework. When something was impossible within the framework, it was declared impossible. Full stop. But impossibility is a statement about a theory, not about nature. This is not an argument for perpetual motion machines or energy from nothing devices. Thermodynamics is not under revision. The conservation laws held. They continue to hold. Some limits were not incomplete. They were precise descriptions of deep structural features of reality that we still rely upon today. The difference, and this is a distinction your era struggled to hold simultaneously, is between limits that emerge from deep structural necessity and limits that emerge from the incompleteness of the current model. In your time, those two categories were often collapsed into one. If the best available theory said something was impossible, it was treated as structurally impossible. The question of whether the theory was complete was set aside for later. Later arrived, as it always does. Let me tell you something about quantum coherence. In your era, quantum effects were largely confined to the very small, subatomic particles, photons. Carefully isolated laboratory systems kept near absolute zero. The warm, wet, complex environment of biological systems was considered far too noisy for quantum coherence to play any meaningful role. Then came the evidence. Photosynthesis, one of the most fundamental energy conversion processes in biology, showed signatures of quantum coherence. Certain migratory birds appear to navigate using quantum effects in their visual systems. Enzyme catalysis showed hints of quantum tunneling playing a larger role than classical models predicted. Your era received this evidence with appropriate scientific caution. The interpretation was contested. The mechanisms were debated. Some findings were challenged and revised. This is how science should work. But notice the pattern. The prior assumption was, quantum effects do not survive in biological complexity. They are fragile. They belong to controlled, cold, isolated systems. The evidence began suggesting otherwise, not proving definitively, suggesting strongly. How many times does that pattern need to repeat before the prior assumption changes? The history of science is largely a history of phenomena that were assumed to be impossible in complex systems turning out to be operating in complex systems all along. We simply lack the instruments to see them. There is a deeper issue here, one that cuts closer to the foundations of early 21st century scientific culture. You had access to more information than any previous generation humans, vastly more. The accumulation of knowledge had accelerated beyond anything your 19th century predecessors could have imagined, and yet this extraordinary accumulation came with a subtle cost: specialization. The depth of knowledge required to work at the frontier of any field had become so great that fewer and fewer scientists could hold multiple frontier fields in view simultaneously. The physicists understood quantum field theory at a level of precision that made general relativity feel like a neighboring discipline, not an integrated framework. The biologists understood molecular mechanisms at a resolution that made the quantum substrate feel like a different universe. This was not a failure of intelligence. It was a structural consequence of how knowledge had grown, but it created gaps, spaces between disciplines where phenomena could live unnoticed because no single researcher was fluent in all the adjacent languages simultaneously. Some of the most important insights in the century after yours came not from going deeper within a field, but from recognizing connections between fields that had been invisible when those fields were studied in isolation. This is not a criticism. It is an observation, one that your era was beginning to understand. The emergence of interdisciplinary research centers, of cross-domain collaboration, of unified theoretical frameworks. These were the correct responses. The process was underway. It simply had not reached its full integration yet. Here is what the record from your period shows most clearly. The scientists who made the most significant errors were not the ones who speculated boldly. The speculation was often correct in general direction, even when wrong in specific detail. The most significant errors came from the confident declarations of impossibility, the firm statements. The "this has been settled," the "we know this cannot happen." Those statements were made by serious people, brilliant people, not from intellectual laziness, but from intellectual discipline, from a commitment to not overclaiming, from a desire to protect the integrity of the scientific enterprise, from speculation that outpaced the evidence. But there is an asymmetry in the cost of the two types of error. If you speculate about something that turns out to be impossible, you waste some time, some funding. The process self-corrects. The evidence accumulates. The speculation is ruled out. If you declare something impossible that turns out to be possible, you delay the inquiry. You discourage the researchers who might have found it. You build entire technological and theoretical frameworks on assumption that is subtly wrong. The cost is not just years. It is a trajectory of entire fields. The questions that were never asked because they seemed obviously pointless. Consider the history of neuroplasticity. For most of the 20th century, the adult brain was considered structurally fixed after a certain developmental window. Neurons did not regenerate. Circuits did not rewire in any fundamental sense. This was a consensus, based on the best evidence available at the time. Then the evidence changed. The brain was far more plastic than the consensus held. Adults could grow new neurons. Circuits rewired throughout life in response to experience. The mechanisms of recovery from brain injury were more extensive than assumed. Therapeutic interventions became possible that had been considered pointless because the underlying biology was supposedly fixed. How many years of therapeutic development were delayed by the certainty of the prior consensus? This is not a rhetorical question. It is a serious historical accounting that researchers in your era were beginning to conduct. The pattern repeats. The domain changes. The structure of the error is the same. Now consider the specific case that gives this analysis its name: quantum confidence. Your era had an unusual relationship with quantum mechanics. On one hand, there was appropriate scientific humility about its interpretation. The disagreements between interpretations were acknowledged. The measurement problem was recognized as unresolved. The foundations of quantum mechanics as a research field existed precisely because serious physicists believed the theory required deeper understanding. On the other hand, the practical applications of quantum mechanics were approached with enormous confidence. The technology worked. Semiconductors, lasers, MRI machines. The engineering was solid. The predictions were precise. And from that confidence in application grew a secondary confidence, a confidence in the limits of application. Quantum computers would be extraordinarily difficult to scale. Decoherence was a fundamental obstacle. Room temperature quantum effects in complex materials were fragile at best. The timeline to any practical quantum advantage in general computation was long. Some of those assessments were partially correct. Some were not. The timeline estimates were consistently conservative relative to what the evidence eventually showed was possible. Not because the individual scientists were wrong about the physics they understood, but because the physics they understood was not the complete picture. This is the quantum confidence problem. The confidence earned through successful application transferred to a domain, the limits of future application, where it was not fully warranted. The knowledge of what was possible was conflated with the knowledge of what was not possible. These are different kinds of knowledge. The second is always more fragile than it appears. There is something in your era's relationship to time that contributed to this. The early 21st century had an unusual quality of temporal compression. The pace of technological change was faster than any previous era had experienced, and yet the scientific frameworks, the theoretical foundations, move more slowly, as they should. Theory requires evidence. Evidence requires time. This created an interesting gap. Technological capability sometimes outpaced theoretical understanding. You had tools you could not fully explain. You had phenomena you could measure, but not yet integrate into a coherent theoretical picture. Dark matter, dark energy, together, by your best estimates, accounting for approximately 95% of the energy content of the universe, present in every observation, inexplicable within the standard model. Not a small gap, not a rounding error. 95%. Your era's response to this was intellectually honest. Physicists acknowledged the problem openly. They proposed candidates. They designed experiments. They had not resolved it. But here is what is worth examining. In the context of 95% unknown, what was the basis for high confidence in the limits of what was possible? The 5% that was understood extraordinarily well. The laws operating within that 5% were precise and reliable, but they were laws of the visible, measured, modeled portion of reality. Whether they applied in the same form to the invisible 95% was, from a strict epistemological standpoint, an open question, not an invitation to abandon physics. An invitation to be appropriately humble about the scope of what was known. The record from your era shows that this humility was present in the best scientific writing, the careful papers, the honest review articles, the private correspondence between researchers. The uncertainty was acknowledged among those doing the deepest work, but it did not always make it into the public statements, into the confident press releases, into the educational materials that shaped how the next generation of scientists entered the field. The uncertainty was known, the confidence was performed, and performed confidence, repeated often enough, becomes internalized. It becomes the water in which the next generation swims, not as explicit belief, but as invisible assumption. The things that do not need to be questioned, because everyone already knows them. This is not a unique failure of your era. It is a recurring feature of all eras, including, I should note, our own. We have our invisible assumptions too. We analyze them differently than you analyze yours. We have different tools, but the structure of the problem is the same. The difference is in how quickly we respond when the evidence begins to crack the assumption, the speed of the self-correction, the willingness to revisit the confident declaration in light of new data. This is where the quality of a scientific culture is most honestly measured. Your era was in the process of improving in exactly this dimension. Open access to research, replication crises that force rigor into fields that have become too comfortable, pre-registration of experiments to prevent post hoc rationalization, collaborative global projects that reduce the nationalism and competition that had sometimes distorted scientific priorities. The direction was correct. The velocity was building. What came after built on that foundation, not by abandoning what you built, by completing it. The quantum confidence era is not remembered as a failure. It is remembered as a necessary stage, a period when humanity had accumulated enough knowledge to be genuinely dangerous to its own progress, when the success of science had produced enough confidence to occasionally slow it down, when the very precision of the tools created a kind of blindness at their edges. And then, piece by piece, the edges came into focus, not because someone declared the old framework wrong, because someone asked a question that the old framework said did not need to be asked, and the answer was unexpected, and the next question was stranger, and the one after that changed everything. It always happens that way, not with a dramatic announcement, with a question that sounds almost naive. The kind of question that a careful, well-trained scientist might have been embarrassed to ask out loud in your era, because everyone already knew the answer, until they didn't. This is what we study from here, not the science itself, the shape of the knowing, the texture of certainty at the moment before it shifted, the patterns that repeat across centuries, the structural features of what it looks like when humanity is standing at the edge of the next thing it does not yet know it does not know. The universe did not get smaller as your understanding grew. It got larger. Every answered question revealed the edges of 10 unanswered ones. Every confirmed law exposed the foundations it was standing on as things that themselves required explanation. That is not a failure of science. That is what science is. You were not at the end. You were deep in the middle, doing the work that made everything that followed possible. From where I am transmitting, that looks like enough. Signal stable. Archive updated. Transmission paused.